second session of Jesus Franco, who's going to talk or continue to talk about perspectives on the astrophysics of dark matter. Thank you.
Thanks. Yes, so I will continue where I left before the coffee break. So just to summarize, what I was implying earlier is that there is on the one hand the possibility that this new dark matter physics exists and it impacts galaxy formation. That's simply just saying that it's allowed by observations. And then there is this other set of problems or challenges that we see in galaxy formation and evolution that might actually be connected to this new dark matter physics. So these are two, in a way, unrelated issues. So when I started giving talks about this, I was always trying to motivate these models based only on these problems. So they were supposed to be just seen as a way to solve these problems. I think now I see them differently. I think these models are interesting on themselves without these problems. These are additional motivations, but they are of course relevant for galaxy formation and evolution. And these problems, as I said, they are essentially connected to the abundance of galaxies and the structure of galaxies, in particular dwarf galaxies. And they have to do with how many of these galaxies we see and the kind of dark matter densities that they have in the inner regions. And these problems could, as I said, be related to either a primordial damping of these initial conditions that I was mentioning before, or if you want a primordial scale of galaxy formation that is connected to the dark matter nature, or it could be a sign of self-interactions as well. And I will show in a second how that is. These are essentially cartoons, but they really, I could show you, I could give you the reference where this is quantified, but I think this illustrates the point just more clearly. Once you include these interactions, what happens, for example, for the abundance of halos, this is again the abundance, this is from a simulation that we did in 2014. This is the abundance of halos as a function of mass, and these models have this interaction between dark matter and dark radiation. So they have these dark acoustic oscillations that I was referring to. And in particular, they have this suppression on the power spectrum. So that's the key feature here. So CDM again predicts this strong abundance, basically continues rising towards lower masses, but these models of course suppress the formation of these halos. For example, this one here, you have these dark acoustic oscillations that actually leave an imprint on this plot, so you can see kind of some wiggles here that are connected to those oscillations. So in a way, there is an imprint, a signature of this new dark matter physics here. And of course, by reducing the abundance of structures here, you solve these problems. As I say, you can quantify it. It's not fully solved. It's not completely solved. It's not solved in a way that is entirely completely self-consistent, but it clearly points towards a way to solving it. And so you can do that on one hand, and on the other hand, if you now have interactions between the dark matter particles, what happens, as I was saying before, is that you reduce the inner densities of dark matter halos. And because of that, instead of having something like this is again the enclosed dark matter mass in a simulation, for example, CDM, and then you take the substructures here, so this is basically the same plot that I explained here. It's just a cartoon. For CDM, you have something here that is very dense, and the Milky Way satellites, the observations tend to live somewhere here. So a way to reduce this density is simply invoking these dark matter collisions that tend to create dark matter cores, reduce the dark matter densities, and you are automatically more consistent with observations. So as I said, this is just a cartoon, but we have quantified this And I think towards the end of the talk, I will show one of these. So these new interactions can certainly solve these issues, or at least the most fair thing to say is that they fare much better than CDM. That's perhaps the best way to put it.
Sorry. Do
Yes.
you know how this additional interaction affects the other observation about mathematics?
Yes. So all of these affect only very small scales. So there are two distinctions, because you have this additional dark radiation, then that can impact some observables in the early universe, such as the CMB, because you have an additional source of dark radiation and actually can perturb the power spectrum that you see in the CMB. So the model that you put here has to be consistent with that, and all the models we consider are consistent with that. Now, that's in the early universe. In the late universe, or our universe today, those interactions, these ones, only have an imprint on small scales. So that what I mean by small scales is scales at the order of 10 to the 10 solar mass and below. And those are not yet proved by observations, right? There are some constraints, but they are weak enough that they allow these possibilities, but that's another constraint. And finally, of course, this type of plot that I put here, if you put a cross-section that is very, very large, of course you are going to decrease the density so much that it's going to be inconsistent. So that's another way of constraining it. In addition to that, really the large scale of structure of the universe looks exactly the same. And that's really the strongest support for CDM as a structure formation theory comes from large scale structure. And all of these models have exactly the same large scale structure. They have no impact at all. So now I mentioned that these problems or these challenges that we see at the scale of dwarf galaxies could also be related just simply to the complexity actually of gas and stellar physics. So most of what I have said relies just on saying something about dark matter, but of course what we observe are galaxies. And I mentioned earlier that for dwarf galaxies, because you have this strong dominion of dark matter, you expect these formation processes to have a minimal impact on the dark matter distribution. And it is true that it's minimal compared to larger galaxies, but it's still strong enough that you have to take it into account. And this is an illustration of that. One of them has to do with the heating of gas that comes from the background radiation that is produced by the first generation of stars and galaxies. So this is a high redshift, say at redshift 10 or so, between 10 and 5. That first generation of galaxies produces this background radiation and essentially heats the gas. It ionizes the gas. And by heating the gas so much that essentially it doesn't have time to cool down until today. So that means that if you have, again, this abundance of halos as a function of scale, well, this is rotational velocity, but this is basically mass. Again, you have your CDM model that gives this strong production of, or prediction that there should be halos here. But of course, not all halos have galaxies. And this effect that I mentioned actually impacts the formation or suppresses galaxy formation very strongly once you reach 20 or 30 in this scale kilometers per second. And if you see in this problem here, well, you cannot see in this one, but sorry, I have to go back quite a bit. No, I just, well, this is roughly, I think this is 60 kilometers per second or so. So this is a mechanism that actually helps to reduce the abundance of galaxies that we observe. So in a way reduces the number of visible halos. Of course they are there still according to CDM, but you just don't see them. So obviously when you count galaxies, it's not fair to compare CDM directly, right? So that's one thing you have to take into account. And another one has to do with heating as well, in this case even of dark matter through supernovae. So what I mean by heating here is the following. So imagine that you have, here is your dark matter distribution, And in the center, you have a dense cloud, which is going to be, you're going to form your galaxy out of it. And that region is going to form a star. So you have a dark matter particle here, and it feels the potential here. And suddenly this star-forming gas forms a star, and after some time, that massive stars die and become supernovae, and you have an explosion. So you have a bang here, and that explosion essentially means that you remove the gas that is in the center of the system very quickly. So it's a process that basically changes the gravitational potential very quickly. And when you take that into account, it's an impulsive, basically it's an impulsive effect, and that's irreversible. So you take this impulsive effect, and by reducing the gravitational potential in the center, this dark matter particle feels less gravity. And it feels less gravity because the dynamical time of this particle is much larger than the time of the explosion. This is what I mean by impulsive. So it feels suddenly, right, this removal of gas. So it migrates outwards. And it stays there, basically. So this is the heating that I'm talking about. So supernovae can actually expand the orbits of dark matter particles and reduce the density of dark matter in the center. So this is a very important effect that can help for this second problem here, because this is just a CDM prediction, but once you put supernovae, in principle, this could also go down because of this effect. Now, as I said, these mechanisms, we know that they are there, but we don't know how efficient they are. And this is really where the key relies, the key is whether or not this mechanism would be enough for CDM to accommodate these observations. I just will say 2 points of why I think this is challenging. So there are several groups in the world. Some claim that both of these problems that I mentioned can be solved, or that there is a way toward solving them. Others say it's much harder. I think that at the moment it becomes, it's still unclear whether you can do it or not. But I will mention 2 points why I think it's very hard. So regarding this issue of the background from the first generation of stars, there's this paper that came out actually like a month ago. And this is again this abundance of galaxies as a function of mass, of rotational velocity, and these are the observations, the CDM prediction here without taking into account that heating. When you take that into account and also supernova feedback, you actually reduce the prediction, but only more or less like here, and maybe with all the uncertainties that we have in these processes, maybe here, but you still have to fill this gap. So this is really, really challenging. So we have to, maybe there is a way, but it's just physics that is so poorly known still that we don't know really how to accommodate this. So this is still an issue. Now the other one is connected to whether or not supernovae are able to solve this core-cause problem or reduce the densities of dark matter halos. This plot shows, it's a bit complicated, but this is essentially the slope of the density profile of dark matter halos measured at 500 parsecs as a function of mass. So this is just a proxy of these inner densities, if you want. And these are simulations that include only dark matter, so those are the symbols here. So this would be the predictions of CDM without this supernovae effect. And it basically matches this NFW profile, so what you would expect just by a simple NFW analysis. When you include the supernova feedback, you reduce this alpha, and that just simply says that the slope gets flatter, so you create cores, but you create them only at certain scales, around 10 to the 10 and larger. Here you can create cores, but here is very inefficient. You see, you stay basically as you would stay in your dark matter only simulations. And the reason for that is that it's very hard, it's simply an energetic argument. So you need enough energy in your stars to heat the dark matter. And in a galaxy, as you go lower and lower mass, you have, as I said, galaxy formation is very inefficient at low masses. So you have less and less stars to form the supernovae that you need to create a core. So if you find systems here, observed systems that have cores, then I would say that that's a that would be almost impossible to solve within CDM. So let me say that again. If you find a very small dwarf galaxy that convincingly has a core, then that would be a very, very serious problem for CDM. But right now, we don't have that evidence because, as I said before, it's very hard to actually say if a system is cored or not. So finally, I wanted to mention a couple of observations that could actually have some clues, can actually be related to new dark matter physics, which I just think they are interesting, but on themselves they don't say anything really. This is just a curiosity. So don't take this as of course as proof of nothing, of anything. One of them is an observation of a cluster. So this is a cluster of galaxies, and you can see here the gravitational lensing again of a background galaxy. And this cluster of galaxies has 4 elliptical galaxies. Now, people doing gravitational lensing have become so good at this, at reconstructing the dark matter distribution using lensing, that they are able to reconstruct the dark matter distribution here, and the positions of these elliptical galaxies and the dark matter distribution within those elliptical galaxies, that they can measure an offset between that dark matter distribution and the stars in the elliptical galaxy. An offset that is of the order of 1 kiloparsec, 1.5. So this is a tiny, remember this is a megaparsec scale system, so it's a very massive system, and what they see is that the stars are separated from the dark matter. Now that's weird because, as I said before, if you believe that CDM is collisionless, it should behave as the stars, which are also collisionless. Right? The probability of stars colliding in these systems is extremely low. So why is there an offset between the stars and the dark matter? And nobody knows the answer yet. If you try in CDM simulations that include baryons, include stars, include everything, you never see this offset. Or you see it sometimes with a probability that is very, very, very small. Does that prove anything? Of course not. It's just one single system. But if you can interpret this offset as dark matter collisions, it turns out that the amplitude of the collisions that you would need to explain it is of this order. So the order of interesting self-interacting dark matter. So that's one, which I think is just something to keep in mind. Later, if this offset is really ratified and more systems like this are found, then it becomes interesting. Right now, it's just a curiosity. Another one that is probably a little bit more interesting, or at least more firm, has to do with the shape of the gravitational potential in our own galaxy. It turns out that you can reconstruct the gravitational potential in our own galaxy very precisely by looking at tidal stream of stars. So this is a picture of the northern sky, and you can see of stars in the northern sky, and there are some streams, they are called tidal streams. This is the Sagittarius stream, this is another stream, another one. So this is basically stars that have been ripped apart from satellite galaxies that fell into our own Milky Way because of the interactions with the disk of the Milky Way. So these streams, as they are removed from the satellites, they are basically tracing the gravitational potential they are moving on. So by looking in detail at the tidal stream, you can reconstruct the potential, the gravitational potential that you have in there. And this is what they have done here. And I mean, it's a complicated plot, but this is essentially this reconstruction. So this is the perpendicular to the galactic plane, and this is in one of the X, I think it's X, or, well, it doesn't matter, in one of the horizontal directions. And the point is that this potential seems to imply that our halo is quite spherical. At 15 kiloparsecs or so, the sphericity, so one would be perfectly spherical, is of this order. Now, when you have CDM and baryons, you put everything in a simulation. CDM in itself is very triaxial, but once you include baryons, baryons tend to make things more spherical. I can give you details if you want, but the bottom line is that it's very hard to push this above 0.8. And as I mentioned earlier, in self-interacting dark matter, you have halos that are more spherical. So this again could be something to keep in mind. Okay, so I will end these lectures with a perspective. So I have tried to give you this introduction on first on CDM and how we have built a model of structure formation theory based on this assumption. And then in the second lecture, I tried to give you different motivations of why this assumption is not as strong as many people believe for structure formation theory, and why also other alternatives can actually have the potential to solve some problems with CDM. So I think this offers really an opportunity for us to exploit. We have this modeling, we have this uncertainty in how to deal with these processes, we have these challenges, and I think we are in a situation where we can do something different. So when we try to address the problem of unveiling the nature of dark matter, these are the typical channels that we look for particle dark matter. So we have some particle physics here and some dark matter astrophysics here that is usually separated. So you have your particle physics models, and of course you try to find hints in dark matter productions, for example in the LHC or in direct detection experiments, indirect detection experiments. And as I said, typically this is decoupled from the astrophysics. So you have your CDM predictions, and then on top of those predictions, you put your particle physics model, you get a prediction for the signal, and then you look for it. Except, of course, for production, that doesn't really depend on that necessarily. But there is, of course, another possibility that I have kind of been suggesting in these lectures, which is these hidden interactions and how they couple with gas and stellar physics. So you can actually use galaxies as the dynamics of the galaxies as tracers of this new dark matter physics. So this is another channel of probing the dark matter nature. And I think it's a very interesting channel because, contrary to maybe the others, it actually has a very narrow window that will be closed, I think, very soon, or relatively soon. So what I mean by this window is always in the language of structure formation theory or galaxy formation. How can you actually use galaxies as probes of the nature of dark matter? Well, you can only use them really in these two windows, these two kind of parameters that I have put here. One has to do with the cutoff in the power spectrum, or the minimum mass that I have been referring to for galaxy formation. This minimum mass is roughly an order of magnitude. This is the window that we have. If you go above this mass, this is, by the way, the mass, just to be specific, this is the halo mass at redshift 0. So this is just to be clear. Above this mass, the constraints on the clustering tell us that dark matter must look like CDM. Below this mass, essentially irrelevant because galaxy formation is suppressed. So you wouldn't be able to probe with galaxies physics that happens below this scale, dark matter physics that happen below this scale. This is the interaction strength, and again here you have a small window. If you go below this interaction strength, then it becomes essentially CDM. If you go above, then the constraints tell you that you cannot really go much more. So again, this is 2 orders of magnitude and 1 order of magnitude. So this is why I think it's very important to close this window as soon as we can. And this is why for a couple of years now, we have been trying to create a model that will generalize the theory of structure formation. So this is my perspective on how to close this window, is to actually realize that we have the tools and also the computer power to generalize this structure formation theory to be more generic and include models that can actually impact galaxy formation. So the traditional way of talking about structure formation, as I mentioned during my lecture, is to start from the early universe, basically from the CMB, and then you go to structure formation theory and you treat the invisible dark matter and the visible dark matter in a separate way, and the only interaction here is gravity. And the traditional channel is to assume cold dark matter, so gravity only, and then you couple these two together and then you obtain your predictions. But of course there are many possibilities here that could be included in a structure formation that would generalize, as I say, this theory. So this is what we have been trying to do. We call it ethos, by the way, because of this acronym here. And ethos means more or less essence in Greek. So we kind of describe the essence of structure formation when it comes to dark matter. So we have been developing this framework. We have now 2 papers that have been published. You can read them if you are interested about the details, with collaboration with all these people. Some are particle physicists, cosmologists, theoretical physicists, astrophysicists. And these are the 2 interactions that we care about, because as I said, those are the 2 interactions that have an impact on structure formation. So what is ethos? Ethos is a framework that allows you to make a mapping from your particle physics model into your structure formation theory. So say you take your favorite particle physics model, for example, say dark matter interacting with a massive neutrino like fermium. So this is the one that is going to give you the dark radiation, be a massive mediator, and this is what is going to give you the self-interaction. This is just an example. Because this model is going to have some properties, the mass, the couplings, well, this is kind of a detail, although it's important, but it's the ratio between the dark radiation to C and B temperature today. So you have your particle physics model, and then you have to come up with a way to map this into the growth of structures. And to do this, you have to go again, this is related to lecture 1, what kind of equations you have to solve. So you have to go again to this linear regime first. How do you affect the initial conditions? The point where the perturbations were so small, you can actually do this analytically or almost analytically. You don't need embodied simulations to do that. These are the same equations that I showed before for CDM, but they have an extra term. And this extra term is connected with the dark radiation and dark matter interactions. So it's in a way like an opacity. It's the opacity of a dark matter to the dark radiation, because it will essentially make as the dark matter and the dark radiation, the dark radiation will feel this opacity because of its interaction with dark matter. And at the end, this is really connected with the collisional term in the collisional Boltzmann equation, which, in the particle physics. So here is where the particle physics come in these equations, because you need the cross section for the interaction. The amplitude of your, for example, the amplitude of your matrix element is going to be here. When we do this with this kind of models and with others that we tried, what we discover is that what matters for this term really is just you can parameterize, you can transform your particle physics model parameters into a set of parameters here, A and alpha, which are connected to, for example, the angular dependence of your scattering cross-section, and they are connected to, of course, the amplitude. And we found a way to write this in a very simple way. I can give you, again, if you are interested, the details. But the important point to keep in mind is just that it is possible to write these equations in a way that you transform the particle physics model parameters into effective parameters that then you can use to construct your initial conditions for the subsequent evolution that you can follow with embodied simulations. So to be a little bit more specific, what you can do with these parameters is construct the power spectrum, the linear power spectrum, again, as a function of scale. This is CDM. And then these effective parameters basically control how the cutoff in the power spectrum happens, and this, how fast it is, how many oscillations it has, etc., in a way that is connected ultimately through the mapping with your particle physics models. And you also get automatically and in a self-consistent way your cross-section for the interactions as a function of velocity. So this is the dark matter interactions that are going to be important for the evolution of dark matter halos, and this is what is important for the formation of dark matter halos.
This mapping doesn't work backwards, right?
I would say yes. No, it doesn't work. Yes, you're right. What it works and what I think is quite relevant is that the ultimate goal of this is to have, of course, it's gonna be maybe 3 or 4 parameters, but you can just to make it simple. Imagine 2 dimensions. You have your effective parameters, and what you can say, or what we hope we can say, is that you have those 2 effective parameters that are connected with the amplitude, say, of the cross-section and the cutoff in the power spectrum, and then those parameters will have regions that give you the same structure formation evolution. And those regions, through the mapping, are connecting to a multidimensional parameter space that is connected to the particle physics model, and that multidimensional volume maps into these regions. So you will be able to say, if I have my particle physics models that go into this volume, I don't have to repeat the simulation because I know where it's going to lie. So this is the goal. And I think this is why we are very excited about this, because any given particle physics model that basically give you the same parameters would give you the same answer. So as I said earlier, so this is the starting point. This mapping is, I think, very interesting. And then we have basically now in place the way to construct this mapping. And we have the initial conditions for the evolution in the linear regime. But of course, for subsequent evolution, we need to do n-body simulations. And this is what we did. These 2 simulations here show the formation of a Milky Way size halo in CDM and in one of these ethos models. And these include all the physics of structure formation followed with an n-body simulation with an initial condition that is different from CDM in the way I described, and with collisions between the dark matter particles. And we wanted to do this because we wanted to address specifically these problems that I mentioned earlier that CDM has. One is the abundance problem, and the other one is this too big to fail problem, or the density of dark matter halos, this problem that I was mentioning earlier. And an example of these models is here, this ethos 4. There are several here, but just concentrate on the yellow one. So this is CDM. This is a strange way but this is essentially the same plot that I showed before, the abundance as a function of a scale. This is CDM. In this case, it's satellites, by the way. This is the observations, and these are the different models. So you see, as you reduce the amplitude of the power spectrum, so you make a cut in the scales where galaxies can form, then you get closer and closer to observations. And at the same time, because of interactions, you reduce the densities that are inferred or predicted by CDM, you reduce them to something that looks closer to where observations lie. So this is essentially, it can be taken as a proof of concept that within this extended structure formation theory, you can find parameter space, you can have points in the parameter space that give you a much closer answer to the observations relative to CDM.
Sorry, you are not worried about the discrepancy that you find at lower abundances? Yeah, around there.
Here?
Yeah, exactly.
Yeah, no, I'm not so worried about that, because here you can see here the number is essentially 1 or 2. So it is really very low number statistics if you want. And the Milky Way halo is just one single system, and this is just a realization of a random system of that mass. So if I could make 1,000 simulations of this, then I would find a distribution here that I would find examples where I find this point. But as I get closer and closer here you have much larger systems, so this would be more robust. So this, in a way, another way of saying is that this is really very low number statistics, so you cannot really, this has kind of an error which is kind of Poisson related, right, which is very large. Yeah.
What is the main change in between the ethos 1 and ethos 4, for instance? Just going
The main change, you can see here, there are huge changes both in the cross-section and in the power spectrum. So you see, for example, ethos 4 has a power, a scale that happens at larger k than ethos 1. So that means that ethos 1, the red one, has a much stronger impact. And that's why you get very, very close actually to the data. But if you look closely here, you actually reduce the density so much that you wouldn't be able to explain these systems here.
But when you translate to the particle physics, for instance, what would be the main parameter? The cross-section between dark matter and dark matter?
Yes, so at the end would be the couplings, the masses that mix to give you this cross-section.
And you are increasing the cross-section for self-interaction dark matter, or?
You are doing both. They are very, they have opposite effects. So if you see this one, this reduces the abundance of structures and has this kind of cross-section. So it's kind of in between. But the blue one, for example, has a larger cross-section but a smaller impact in the power spectrum. So they are kind of combined. We were just exploring the different possibilities. I'm close to the end here. So as I mentioned earlier, of course, all of these that I mentioned so far, and we have developed ethos really only until the point where we only consider dark matter, and we have created this mapping between dark matter physics and structure formation theory. But of course, we have to move beyond that to actually incorporate baryonic physics in a way. There are two reasons for that. One is the obvious one, of course, we observe the galaxies and not the dark matter. But there is also, let me stop there because the other one is more a sociological reason and I don't want to get into that. But we have actually started exploring this. So this shows a simulation that has actually baryonic physics with dark matter interactions. So there is a galaxy there being formed and it has hydrodynamics, radiative cooling, stellar population, supernova feedback, etc., etc. So it has all the ingredients. And we found something interesting. If you make a plot of the density as a function of radius, for dark matter, I explained this many times already, compared to CDM, the interactions, and let me just be clear again, this is just dark matter interactions. These don't have dark radiation. So as you put that interaction, you decrease the density. So this is the story that I was telling before, and the way you decrease it depends on the amplitude on the cross-section. But curiously, the stars, well, maybe not so surprisingly, but one thing that we confirm is that the stars basically follow, because they feel this change, they track the changes in the dark matter distribution, and they are distributed in a way that mimics the decrease here that you see connected to the amplitude of the cross-section. So in a way, it could be that there is a signature of dark matter collisions in the stellar distribution. So that's one of the predictions within this specific model that we tried. Now let me end. How much time do we have? Sorry.
25 minutes.
Well, that's plenty of time. So let me. This would 20 minutes. Okay. Yeah, I think I'll take probably 10 minutes only. Let me just end with a couple of words about some challenges that I think are very important, that are really that we have to address if we really want to close this window that I was mentioning before. And they have to do with the strong interplay that happens between dark matter and baryonic physics, because once you include baryonic physics, as I said before, for example, supernova can create a core, and also the dark matter collisions can create a core. So how do you distinguish one of them? And another problem is something you can see here. So this is a plot that shows the dark matter density as a function of radius. So this is the standard density profile. And this is a simulation where you put dark matter in CDM and self-interacting dark matter, and then you put a galaxy by hand. So this is not a full simulation because it would be too expensive. But you put it by hand just to see what is the dynamical impact on the dark matter distribution. And you see, I want to just emphasize one complication that becomes very apparent. So if you would just deal with dark matter only, then the story would be very clear, very simple. CDM would be NFW-like, and then self-interacting will have this core. But once you include the galaxy, it depends. This is essentially a Milky Way-sized galaxy, but with different degrees of compactness, if you want, of concentration of your distribution of stars. So one is very extended, the other one is in between, and then one very, very compact. So when you put the extended one, what happens is you are putting basically a galaxy in the center that is quite massive. So it moves the distribution of dark matter towards the center. So this is something that I mentioned in my lecture yesterday. So the CDM becomes denser, but also the self-interacting dark matter, but the relative difference between the two gets smaller, but again, you have CDM being denser, more dense than self-interacting. But as you make it more and more compact, the situation reverses. And the reason for that is that if you make it really, really compact, then the self-interacting dark matter core actually responds much more dramatically than your NFW or your CDM model. So you could see there is a clear degeneracy, because depending on the size of the galaxy that you are dealing with, even if it's the same mass, you are going to predict something different. So that's a challenge. And the second challenge, which I think might hold the key to really make progress here, is the following. So I mentioned that it is possible to create cores in dark matter halos through supernovae and through collisions. So in mind, you have these two processes, and you wanna test which one is the real one. Maybe both. That would be kind of a nightmare. But let's say you want to distinguish one or the other. Here you see a set of simulations that one has CDM, and it creates a core. So this is the size of the core as a function of time. And it creates a core because of this supernova feedback. And you see these simulations have, essentially you start with something that basically doesn't have a core, and then you have a supernovae or a series of supernovae events that start removing gas from the center and create the core. And you know, they are all doing like this because these are very explosive events. And you end up with a core which is of the order of, say, 1 or 2 kiloparsecs. In the case of collisions, you can actually get also something which is of the order of 1 or 2 kiloparsecs, with 1 centimeter squared per gram, but you create it very differently. It's almost adiabatic in the sense that the response of the halo to the collisions is very, very gradual and smooth compared to this burstiness that you see here. So I think there is a key here, or there might be a way to make a distinction between these two processes because they are different in nature, although at the end they give you the same answer. So this is the hope. How can we actually distinguish these two? So I will, I think, end here just with some remarks. I think, as I said before, there is an opportunity to try to address the problem of the dark matter nature with structure formation, and by that I mean with galaxy formation, because after all we know about dark matter comes from gravitational evidence, and most of it, or a large part of it, comes from actually the dynamics of galaxies, the dynamics of clusters, etc., etc. So it might be that there is actually a clue also of the properties of the dark matter particle in the dynamics of galaxies. And the only way we can really see if this is true or not is to generalize this structure formation theory. And this is what we are trying to do with ethos. And the thing that I would emphasize about this framework is this, that it creates this mapping, just to summarize what I said before, it allows you to go from your particle physics model into your structure formation model. And it would, hopefully we will be able to make these regions in the parameter space that connect the two in a way independent models. And again, to emphasize that this is a relatively narrow window that is just there for us to reach, and I think it might be possible to close it soon. And the final point that I want to make, that I have heard some people complaining about this, and I will close just with this a comment. This is a personal comment. It is often that I hear people mentioning that, you know, you have CDM model that works actually quite well. It has some issues. It doesn't have any parameters when it comes to structure formation, so it's free parameters, 0 free parameters. And then with these models, you are adding parameters to your structure formation theory. So, of course, in a way, you will be able to get a better matching just because you are adding free parameters. So many people are, they don't want to move beyond that simplicity. But to me, it's hard to argue that simplicity because a structure formation theory is not a full dark matter theory. You cannot say, this is my dark matter theory without saying something about the particle physics. And then I think it's unfair to say that a model is simple if you don't go to a higher level of your theory, which is your actual particle physics model. So structure formation is, in a way, a lower level of your dark matter theory, and there is where I don't think is fair to say that this one is more simple than this one. And any degeneracies that you have, because you are adding these free parameters plus the baryonic physics, that means that your complexity is increased, I think is essentially unavoidable, and we have to deal with it. Thank you.
Well, now we have plenty of time for questions and discussion.
Could you define MCUT? I'm not sure what is the meaning of MCUT. What does it mean, MCUT?
Yes, I can say more precisely. So this is the mass of isolated halos, so not subhalos, halos, today. So this is essentially that mass below which you would have a cutoff. So you basically remove the structures below that mass. This is a rough, of course, this is a rough cut.
Is the mass of halos in which you can test the self-interacting dark matter hypothesis?
Yes, so this would be...
That's what it means?
Yes.
Okay.
As I said, above this scale, it has to look like CDM. You cannot have a suppression. Below, you cannot probe it. You cannot test.
Why not?
You cannot probe it because below this scale, if you have a cutoff below here, you could essentially have, below this scale, remember this is again isolated halo, so below this scale, galaxy formation is highly suppressed, so you don't have galaxies below this scale. So you cannot see those galaxies. Yeah.
There's another question in the back.
Yes. There is another effective field theories in cosmology, for example, for inflation. In that case, you have a breaking of diffeomorphism, and that generates a Goldstone boson, etc. In this case, in your case of this effective field theory, there is nothing fundamental happening behind this new set of equation, or is it just a new parametrization of your variables? Or
Yeah, it's just really that. I mean, the name can be misleading. I mean, this is effective, but it has nothing to do with high energy physics or effective field theory. This is, we call it effective just in the very simple terms. These are really just a way to parameterize your theory with these effective parameters, right, that control basically everything that you need to know that is relevant for structure formation. So this is where the effective ends. There is no connection beyond that. It's just a name.
So then when you have, for example, a matter power spectrum, from there you can infer the microphysics of your models. I mean, what kind of interaction the dark matter have, or?
Well, as we were mentioning before, I mean, the reverse mapping is not clear. So you could have many models, many parameters here that would give you a power spectrum that is actually quite similar.
Yes, but a kind of.
What you would be able to say, if, let's say, ideally you can say with observations, this is the power spectrum, this is my transfer cross-section, then you could go back and just get this volume in this parameter space where the theory is, right? But it's still going to be a large volume.
So you're going to have a family of
exactly
models.
Yes.
Just a last one, sorry. The time of where dark photons decouple from the dark matter is the same as photons of the ordinary matter?
No, it's not the same.
When occurs that?
So what controls that is basically the mean free path between the dark radiation and the dark matter, and that's connected with what would be the analogous of the Thomson cross section, both for dark matter and dark radiation, and that would be connected to your couplings and masses, etc., etc. Right?
But they also are going to depend on the dark matter model.
Yes. Yes. But because of the constraints, I'll have to go way back. But because of the constraints, you can only you can see here. But because of the constraints, you cannot go at larger scales. So this is basically this is related, right, to this decoupling of the photons and the baryons, and this is related of the coupling between the dark photons and the dark matter. So you cannot push this here because it would violate the constraints. Yeah.
Thank you.
More questions, comments?
So just before you started the third lecture,
Yes.
you mentioned this little offset between the
Yes.
center of the star and this. So,
Yes.
and you said if you see the offset, you can do the. Can you do the reverse, that if you don't see an offset, would you say there are no new physics interactions?
No. The reason is so.
Or limit the interactions, I mean.
You can definitely put very strong constraints on the amplitude of the cross section at the velocities that are characteristic of these systems. So at very large velocities. So yes, you would basically suppress the possibility here. Let me see if I have it here. I have to go way back here, right? So if you measure, say, sub-kiloparsec, if you don't see sub-kiloparsec offsets, right, this probably would go an order of magnitude here. That's roughly, this thing is compatible with offsets of the order of, as I said, 1 kiloparsec or so. So you would decrease it roughly by 1 order of magnitude. Yeah. But you still have all this. Yes.
So in your ethos project, suppose you now have it under control, what would be the next step? Would you add dark matter baryonic interaction, say, could be only loop level if you're talking about particle physics?
So I think we have two important tasks that I think would essentially complete the framework, in the sense that, well, let's say it will complete the framework to my satisfaction in actually having to really say that, to erase this towards here and say that we have this effective theory, would be to add, of course, have a way to connect these two, And this is a very hard problem because, of course, people have been trying to do this between CDM and normal matter for 20 years or so, and they still haven't succeeded. So we can do two things. We can either copy what they have been doing and then be happy with it. I'm not happy with it because it has some problems. The alternative, instead of trying to solve the whole thing, is just to try to solve the issues that are connected between distinguishing dark matter and baryonic physics, and this is connected again to the last slide that I showed. So if we can implement a way of dealing with supernovae in a way in the simulations that can distinguish these two, and is not very sensitive on how you do it, then I would be happy with that. And then I would call it that we have something that is more or less closed. So this is a direction that we are working on. And the second has to do to try to integrate more models into this framework. So right now, they are basically all around this type of thing. But there are other possibilities, of course. And there is also the issue of something called inelastic dark matter, in which case you no longer have just elastic scattering, but inelastic, when you have multiple states of dark matter. So you have an excited state. That's also something we are working on. And I think when we add those two things, a more generic treatment of this in a more or less robust way of including baryonic physics, then I think we'll have a framework that I would be happy with.
More questions?
The main photons, it's because it has to do something with the electromagnetic photons, or it's just any kind of interaction different?
Yeah, I mean, of course it's a different interaction. I mean, it's in the dark matter sector, so it's just analogous in the sense that in the simplest scenarios, you can think of dark matter as being charged, but of course in the hidden sector, right? And then you will have, in principle, massless mediators, which would be massless like the photon, but in your dark sector, right? And then you have something analogous to the Coulomb interaction, but in your dark. So I think this is where the name comes from. But yeah, that's just an analogy to the standard model. Yeah.
So it will be an attractive and repelling interaction?
Yes, in principle, yes.
More questions? No more questions. Everybody seems to be hungry. So let's conclude the session with a big applause for Jesus for this nice series of lectures. Perhaps Miriam has announcements? No? What time do we come back? At 3? Sorry? So, at 3? So we come back at 3:30. 3:30 sharp. Okay, very good. Enjoy your lunch.